Okay, we're recording. Hi, everybody. All right, anybody shy? Sorry.
Oh wait, it's not. Is it web?
Oh, it's not web. It's not live.
Okay.
I can blur your face out if you want. Too much work. Okay.
We were all waving.
Yeah. Okay, so this exam's coming up Friday, so be aware that there's a bunch of different things you could do. So if you're someone who's feeling behind, there are a bunch of worksheets here that go through the basics above and beyond what the discussion sections do. There's all these guide links. I expanded these pretty recently. Uh-oh, no internet. Well, it'll be there. Oh, there we go. That was cool. What? That was strange. It's still not connected. I don't know what just happened. That was cool. Anyway, there's these guides, which sometimes there's an overview, but nobody seemed to be +1ing this so much, so whatever. But there's a whole bunch of questions here, more than you would ever want to do. I'm not providing solutions just because it takes forever to write them and make them good. But you guys are welcome to write some and put up whatever you want, questions, answers. Yeah, some people in the back, go for it. Anyway, yeah, so there's more practice problems here than you ever really want to do, but if you want more practice, there you go. And if you want even more problems, you can go to Old 61B midterms, but there it's harder to know what counts and what doesn't because you don't know what topics, like even last semester's midterm, it happened later in the semester when I was co-teaching with Paul a little bit, so some of the questions cover topics we haven't covered yet. Anyway, and then I have some general studying tips. But my main suggestion, I don't know if you guys saw my post, but the main thing that you might not have thought to have done is work with other people and watch how they work on problems and have them critique you, and you learn a lot. And as long as you're working with people that you feel comfortable around, it could be very cool. I did that in this one class in graduate school, and I wish I'd known about it as an undergrad. It was like the best thing. Because it's just like, oh, I didn't know that was like a formula you could use or whatever it is. Yeah. Anyway, all right. So that said, this will be our last data structure, our search data structure of the semester. We'll do some algorithms after that and then a bunch of little things. So we will get through this and we'll talk a little bit about summarizing what we've done the last few weeks. We won't cover anything that we'll discuss in lecture on Wednesday on the midterm, so this is the last one, but we will have a little bit of summary on Wednesday as well. All right, so the new thing. This is basically like, I guess, a show of strength. We're going to cover a new abstract data type, totally new, we've never seen before. We're going to see a totally new type of implementation for that data structure we've never seen, and all this is possible because we've gotten some practice with this kind of thing. So the data structure in particular we're interested in today is called the min-pq for now. So this is a priority queue, and you get to give it as a magic, I don't know, sack of potatoes that you toss things into using the add method. So you can put whatever items you want in there. And then you can ask this magic sack of potatoes, what is the smallest thing inside of you? And it'll return that. You can also pull the smallest thing out of the bag, and you can also get the size. So you can think about this as another type of collection, like say a list. So the list, actually let's say a stack. So let's say you have a stack, and you try to get something from the stack. Which thing do you get? You get the the top thing, the most recent thing. Here it's different. Here it's, instead of having like a stack of stuff that you pile up and pull a thing off top, now it's a bag that just magically always returns the smallest thing. So this is obviously handy for a number of reasons, like if you wanted to do like that line at Disneyland where you pay extra money to skip the whole line or whatever. I don't know. Actually, they don't do that. I like the idea like the more money you pay, you get to like skip more lines or whatever. So if you want to implement a line where whoever paid the most always got to skip the line, you could create a line like this, and everyone just shows their badge, and you find out what their cost is. Yeah, that would be a maximum version. Yeah.
And now, what do you do in case the people have equal priority?
So if you had equal, I guess you could break ties arbitrarily. Yeah, that would be the usual strategy, and the one that we'll employ today. So this particular priority queue, or this idea of a priority queue, there's some other things you can use it for that are less obvious. Oh, look, moss. Anyway, all right. That's our thing we use to make sure you're not cheating on projects. So we haven't done that for project 1 yet. So if you cheat on project 1 and you're waiting to get caught, don't worry. Yeah. It's really a bummer. God, this is so high pressure here. It's insane. Anyway, but I guess, did anybody see that thing about 106A at Stanford? They had like a 20% cheating rate. So that was kind of surprising. Because it's a lot easier to get an A there. So, I mean, it really is, honestly. I mean, it's not even like a thing. Yeah. I know a lot of people that teach there. I know most of their crew. Okay, so let's get rid of this. So what we're going to do is we're going to pretend like we're some sort of evil, or I don't know, whatever. Depends on your politics, government agency, and snooping traffic and trying to find the M largest transactions. That is our goal. And so we're given a transaction stream, which is a thing we can iterate through. So we can, for example, say for a transaction T and TS, I don't know, we could print them if that was a thing. And if we try and compile this code, we're not going to actually run it at any point. We're just going to, this is too much cruft here, but what do I want? I need to change my build system, I think. Yeah, just Java. Okay, only compile. So we want to be able to compile this thing and return null. Okay. So what we want to do is be able to return a list of the top transactions. Okay, that's our goal. And we're going to try and use this priority queue idea to find the largest ones. So we need some kind of priority queue. So here we had the notion of a min PQ. We'll also have one called a max PQ with get largest and remove largest methods. So which one would you like to use? Max. Okay, sounds good. So let's create a max PQ of transactions. And maybe we'll call this thing a max, or let's call this all transactions equals new heap max PQ. And heap max PQ, what's that? Well, it's just some implementation that we'll talk about later. And so that creates us our list of transactions. Okay, so after we've created this empty magic bag that always gives us the largest things, and we iterate through these transactions, instead of printing, what do you suppose we should do? Sounds like a good choice, because what else are you going to do? Okay, so we add them to the bag. Okay, we put all the transactions that have ever happened, millions, billions, trillions, whatever, inside this giant bag, and they're all there waiting for us. So what next? So we're supposed to return a list of the biggest ones. What do you guys think? The M largest, specifically, yeah. There's no sub max PQ thing. All we literally get is add, get largest, remove largest, and size. Okay, so let's do get largest. And so we need a list. Yeah, so we'll do largest. You also mentioned making a list. So let's make an array list, let's say, of transactions that is going to be top transactions. All right. Okay. And so we get the largest here, and then we add that, let's say. And then ultimately, we're going to have to return this. So that's some of them. But the problem is we need to do m times. Okay, so, well, all right, so let's do this. So we want m items. I is less than m. I plus equals 1. Okay, so we're almost there. But what's the problem with this? You're always getting that largest one. So the get operation doesn't actually, you maybe call this, it was like peeking inside the bag and seeing this big thing and going, okay, great. All right, elephant. Okay, elephant. All right, elephant. So that's not so good. So what do we actually want to do instead here? Remove largest. Okay. So if we try and compile this, it compiles, except that we didn't actually pick a data structure to remove from. What was it called? All transactions. So we have the big satchel of all of them. Remove, and there we go. So this should work. I'm not running it because we don't, if you look inside the dark secrets of what a transaction is, it's actually just a bunch of nothing. Yeah, whoops, it doesn't do anything. Anyway, so that's transactions. Okay, so this approach, what are some concerns we might have about this? This is kind of an open, tricky, actually first, before I do that, any thoughts about how it works? So this is just taking all items you know of, throwing them in a giant bag, and then pulling out the elephant, then the slightly smaller elephant, then the giraffe, then the rhinoceros, and so forth, until you get down to the small things you care about. Okay, so any concerns or thoughts about this code structure that you would maybe be worried about? Yeah.
So just in general, like for priority queues, like order of when it's been added, like has no.
Yep. So the order in which you insert things, no effect whatsoever. Somehow, we don't know how they're implemented. It's abstract data type though. Yeah.
It seems like maybe one concern is that you're modifying or no. Yeah.
Well, you build those transaction lists and you're throwing them away, right? Okay. So the idea here is that you threw away some of the large transactions, so you don't have them at the end. So from the perspective of this method, why is it not a big deal that you've thrown away the m largest? Well, you iterated through this thing, put them in the top transactions bag, and then you removed them. So why is that not a big deal?
You still have them in the...
Yeah, the stream presumably still has them. So you made this big giant bag that has a copy of every single thing you ever saw. you squeeze out the top things you care about, and then of course you let this thing get garbage collected. So it's not such a big deal that you did that. But there's a related issue, which is that you've just made a big copy of every single item, so that thing is potentially very large. So you've basically made this huge bag, squeezed it just a little, and a few things come out, and then you throw away the whole bag. So I don't like that very much. So is there a way we can keep the bag from getting super huge, wasting all of our, precious space with this huge bag? What's that? Oh, the iterative, some kind of iterative solution. I still want to use the priority queue. Hint, hint. So here, the problem is we put every single thing in the bag, right? Yeah? Say again? Yeah, okay. So what we really want to do is don't add something that is smaller, that is too small in a way. Okay. So how do we do that? How do we find... If it was just maybe to be vague here, if we wanted to track only the small things, or like we could do something where we want to, like that's our ultimate goal. But this priority queue, it only tells us about large things. It doesn't tell us what is the smallest thing in the bag. I guess more specifically, you might say if the item to be added is smaller than m things in the bag, ignore it. Right? So I don't want to add a paperclip to my bag if I already know I have, like, say m is 100, and I already have 100 huge things. I don't want to put the paperclip in. So the crazy thing, the surprising thing, is I can do that by using a minimum priority queue instead. Okay? So I'm just going to kind of walk you through this thought. I don't know how to make this gracefully discoverable. So if I make this a min PQ, I think we kind of did it this morning, but I don't know, it was a little rocky. Anyway, so if we make this min PQ called, instead of all transactions, let's call this largest transactions. Okay, variable names help quite a lot, I've found. And here then, let's say that we want to, if we're tracking only our largest transactions, well, actually, I'm gonna do add t. But the problem is that maybe, at this point, when I add my paperclip into this bag, so say m is 100, and I have 100 huge things in here, and I add a paperclip. Once I've added my paperclip, how do I get rid of it? Let's say. I don't know if I kind of lost you guys there. Yeah, so if I just do this, remove smallest, okay? So if I remove the smallest thing from the bag, then what I think about my bag, I know this bag, actually, let's see, remove small. So that's pretty weird.
Add m first.
Yeah, okay. So what you're proposing then is, yes, what we want to do is add m things first. What's even better than doing that? Yeah, we could check the size. So what I really meant to do, sorry, what we could do is say if the largest transactions, if its size is greater than m, at that point what you're saying is I have too many things in my awesome bag. I really ought to throw away the small one, all right? The other approach that some of you might have thought of is start off by adding m things from the transaction stream, but that will be awkward given this syntax. So what I'm going to do here, so basically the approach is instead of having a bag which gives me the largest things, and I put every single in the bag and then pull out the large things one by one, now I have a smaller bag that I'm going to say I'm only going to allow 100 things, m things, to be in this bag ever, and I'm just going to add things over and over. And then once the bag has too many things in it, I'm just going to keep taking out the smallest, so that I throw in the elephant and the paperclip and the horse and the chair and the whatever else, and then I get like the dust mote is item number 101. So I add the dust mote in the bag, and then I say, bag, give me the smallest thing. It's like, here's that dust mote you just put in, and I just throw it away. And in that way, the transaction bag always contains exactly those transactions, which are the largest. Yeah?
But instead of having to add the 100th one thing and then remove it, can you just have a field that keeps track of what the value of the 100th thing is? So
Okay.
you never even do the add.
That's an interesting thought. So you're saying, though, what we could do, this is an alternate approach, would be if the largest transaction, if largest transactions dot, you want to know about the smallest, right? Yeah, get smallest. If that thing is bigger than t, then just don't do anything, basically. Yeah, that sort of approach would work fine as well. Yeah, but I've just decided to do it this way because it sounds cooler. Yeah, tells a better story. And it turns out to be no more costly. Okay, so before we continue, actually, maybe we'll finish this off and then we can discuss this. So at this point, whenever we go to this bottom part, what do we need to do now? Does this code work? Why not? There's no such thing as remove largest. So what should we do now? Oh, so you're tempted to just return largest transactions, but the trouble is the API says it's not a list. So we still need a list. So how do we add everything to the list that's in there? These are the only operations we have. Yeah, alright, so that's kind of weird, but that's how the API does for us. And I guess this thing is now, I don't know, smallest of the big things. Alright. Because again, I'm a fan of, it's Java. We'll be verbose, we'll live with it. And maybe it's in the wrong order, but that's something for someone else to figure out later. It's the NSA. We got a big budget or whatever. So. Cannot find symbol. Yeah, thank you. Okay, so now it compiles. Okay, so thoughts about this idea, data structure. Yeah.
So what does bottom?
This part down here,
Yeah.
it's just sort of a hack to get everything into a list.
Oh.
Yeah, kind of like when you had the collection numbers in Project 1, you just had to do weird gymnastics with your data structures sometimes. And if the API was stronger, maybe it has a to-list method or something. But yeah. Cool. All right. Any further thoughts? Yeah.
Explaining again, like why you do .remove smallest, or you should just like not add it at all.
So the approach that someone had earlier was don't add it at all. So you could do something like this, like if it's smaller, then don't do it. Like don't do anything. I don't know if you guys, I probably have never mentioned continue. I guess maybe in 61A they mention it, but you could do a condition basically as you proposed. So that's fine. It's just that it turns out that I just like the way this one reads better.
So then the size checks like how many
things are inside. Yep. All right. Cool. Okay, so priority queues. So they're a really neat data type that does a lot of stuff for you that you wouldn't expect, like this. Another thing that it's used for that I find really interesting is event-driven simulations. So if you do bouncy balls of gas particles and you're doing some kind of ideal gas modeling, it can come up in situations like that where you create a priority of the next event that is supposed to occur. So if you're doing some sort of physical simulation in which events can be reliably predicted, it can be a way to speed things up. So actually, maybe to make that just make the tiniest bit of sense, when you guys did the in-body assignment, you had this notion of a time step where you always made everything move by some particular delta time. But when you're doing other kinds of simulations, you sometimes don't even care about the state of the universe in between events that occur of interest. So if you're only tracking collisions, then you can use a priority queue where you only simulate every time there's an actual thing that happens instead of all the moving around. Anyway, that's neither here nor there. Okay, and that's the code version. So the next question is, how do we even build this thing? So we've come to understand this totally new abstract data type, so how do we build one? Well, one approach would be making an ordered linked list. This will be my straw man that I go to first. I always like to pick on something basic. So to add something to an ordered linked list is time in. Why? Yeah, so you go through the whole thing, and then wherever it needs to go, you put it in there. So if I put in, this is the worst case. So if I put in the number, say 1 million, into a list that only has a bunch of smaller numbers, then 1 million has to go to the very end. Okay. How about get smallest? Why is it 1? First one. Why is remove smallest the first? Remove the first one, and then change the head pointer. All right. So what's some other ways we could build a priority queue? All right, a tree of some kind. Okay, so let's say a BST. Okay, so how about a BST? How long would it take to... So now in this case, we're going to build a BST, our magic bag that tracks largest or smallest things. If I wanted to add something to a BST, what's the time for that? Log in, and that's only if we do what?
You make it bushy.
Yeah, okay, so we'll just say it's bushy. Okay, yeah. Okay. How about getting the smallest thing from a BST? What do you think? I mean, yeah. All right. How would you do it? Binary search basically. Go left, though. Okay, so you go left. Actually, side question. The smallest item. I'll save that question, actually, for now. So if you want to remove the smallest, what do you do? How long is it, I guess?
Slightly longer.
Slightly longer, but what's the runtime in big theta? Log in. So you go to the last, and then you delete it. So how many children does the smallest thing have? 0. Can it have more?
Can't have.
It can have a right child, right? Yeah. So it's possible that it has a right child.
But it can't have a.
Can't have a left child. But it should certainly be log n time. Log n to go there, and then you change one pointer. Just whoever's your parent, you point it at your right child, if you had one. All right. So this seems fine. This is a perfectly good representation. For the heck of it, I guess maybe we'll do, I don't know, an ordered array. So this approach is fine, but I have 4 columns here, so let's do another one. Yeah. So you guys jump right to the solution I liked. What? Who? All right. So I want to add something to an ordered array. How long does that take? In the worst case. This is kind of an interesting question. If you wanted to, it should just be, yeah, okay, let's suppose you want to insert something to the very front. What are you going to have to do? Yeah, shift everything over. You could do something crazy, I guess, and avoid the ordered array. I don't know what it would look like. But I think when I say ordered array, I usually mean there's n things in the array and you put it in a particular spot. How about getting smallest? 1. Okay, how about removing the smallest? All right. What's your implementation when you remove the smallest thing? What do you leave in the spot where it was?
Wait, see what?
Oh, so when you remove the smallest,
Okay. Oh.
if this was time 1, what would you, so you go to the position 0, let's say, and what do you put there?
Empty.
So you could, you're saying if, 1, if you leave, I guess we'll call it tombstones of dead things.
Sure.
Yeah, but then you waste memory. What if you don't leave tombstones? N, have to shift. Okay, so it depends on how you implement it. This is definitely more, this is more common, right? Because you want to, it just gets weird. Anyway, it's also not really a good data structure, so I'll make it a weird color. What's the weirdest color? That one.
Red.
Yeah, all right, yeah, cool. All right, okay, so this works perfectly fine, though. That's kind of a side trip here. So this is great, but I'm going to show you just an alternate way of doing it that'll have a couple of advantages, but it won't be an obvious win. But this is extremely, nonetheless, very common. So rather than using a binary search tree, there's another kind of tree you can use that has a neat mathematical duality with the binary search tree, known as the heap. So binary search trees are fine. You have to keep them bushy. We know how to do that. It's not such a big deal. How do we keep it bushy, actually? I should ask you guys. How do you keep it balanced? Well, here, yes, but I haven't told you what this thing is yet. So binary search tree. Let's go back. How do you keep this bushy?
3, 4.
Yeah, do like a 2, 3, 4 red black tree thing, right? So we could either implement it as a 2, 3, 4 tree, 2, 3 tree, or we could implement it as red black tree. And in fact, if you look at tree maps in Java, you'll see that it does this big crazy rotation stuff, right? It has very complex code. Yeah. Okay. Actually, any thoughts about that, by the way? Red black tree? Yeah. No. All right. Cool. Yeah. The key thing that you guys should know about those, by the way, is given a 2, 3 tree, what does the red black tree look like, and vice versa. If you know that and you know how 2, 3 tree insertion works, you're fine. Okay. But this is an alternate approach. This is now a heap. And so what a heap is, it's a different type of tree with 2 particular properties. To be a binary min heap, you need two properties. One, you need to be complete, and I'll tell you what complete means by example in a moment, but it basically just means the tree is very full, so super full. It's not even like slightly off. And it also needs to have this thing called the min heap property, which is that every node is smaller than both of its children. So for example, 0 is smaller than all of these, 5 is smaller than these, and so forth. We have no restriction about duplicates in this tree. So when it comes to completeness, the definition, what it means is that a tree is complete if there are only items missing at the very bottom level. So in this case, this is the bottom level. And all the nodes that exist are as far left as possible. So this one right here is considered complete, even though it has this missing, because the only missing nodes are way over at the right. And this may seem like a very artificial definition, but there's a good reason for it, as we'll soon see. And so this one's incomplete, and this one, it lacks the min heap property. So what here is, where's the problem here? 4 and 5, so these are the culprits. Not so good. This one is incomplete because it's missing something, but it's not, the items are not all the way to the left. So if this were here, it'd be okay. Yep. All right, so that's heap. And it's kind of like the binary search tree property, just a little less strict. You just have to be arguing. I don't know. It seems a little less strict to me, just because all you need to really do is have all of your children be smaller than you. And okay, there's this completeness thing, but how hard is that going to be? All right, cool. Okay, so let's see this in action then. Oh. Okay, close your eyes, everybody. Okay, it's more fun to invent it ourselves. All right. There was a lecture this morning, and I missed that one. Okay, so let's talk about why a heap is any good for this purpose. Given a heap, how do we know, how do we implement a priority queue operation? So if we want to get the smallest, I'm just going to give that one and say we return the root. All right. So why does that work? Why do we know this is good?
So it's guaranteed to be smaller than everything.
Exactly, the heap property. This is basically the heap property. Okay, how about adding something? So let's say we want to add a new number. Let's say -1. All right, and I had this trouble earlier today, but we figured out a solution, which you can see the remnants of, which is white in it. Okay, so it won't quite fit. So here's -1. Okay, so how do we add this thing to our heap? And let's keep in mind that we want to maintain completeness somehow. So any thoughts? Okay, so if we just assume, it would be very cool if we don't have to worry too much about completeness, I would just stick it at the end for now. Now, is this a min heap? No, right? Why? This thing, yeah, it's out of sorts. So what do? We could push it up. So you can basically say, you know what? You're more qualified than your boss. You need to replace the boss. So I will trade them. And maybe I'll write this out. So I've just switched these two. Well, you know what? That was kind of a has. -1. 1. All right. So when we add, we can place the new employee in the last position and promote as high as possible. Okay. Is this a min heap? Right. Those who say no, what's out of work? 0 and -1. Okay, so -1's actually still very qualified. Join the company, but really ought to be taking over this president's job. Okay, here we go. All right, so this is now, is this a min heap? No. Is this safe, this process? Is trading, actually maybe this is just as good as the general question. If I move -1 up here and replace 0, is this definitely smaller than everything over here? Why?
Because it is a transitive.
Yeah, basically you can think of it's transitive, right? If I'm smaller than you and you're smaller than these, well then you better be smaller than all of these. There you go. So that should be fine. So this approach will work well. Okay? And that's really elegant, right? How do you add to a heap? You just stick it at the end and promote. Much simpler than all the rotation stuff we had to do with BSTs. All right, removing the smallest. Well, this is a new problem we have, right? So if we want to get rid of the smallest thing, we want to get rid of -1. So, does anybody have any thoughts about how we might do that? Who's not seen this before? I'll give you a hint, which is that we don't, let's again start with thinking simple, which is to say, let's not ruin completeness.
Can we just do it the other way? Like,
Yeah, what do you mean by add? Yeah.
so like you move the last node to the root, and then like you just swap that.
Aha, okay. So you're saying, take this guy. So we assassinate the president. Oh, not the president of a company, not of the United States. I don't want to, the one time I had government agents show up to my house was plenty of such times. Of my company. Of the company. Alright. Okay. I actually had a dream last night that I was hanging out with Barack Obama. It was very cool. I had a fun time. And then I was thinking this morning, like, I wonder if Bill Clinton's been out of public eyes long enough that I could just be like, hi, I'm a professor at Berkeley. Could I come hang out with you sometime? I don't know. Maybe. I'll let you know if it works. I did also once meet Pitbull, by the way. Yeah. Anyway, in Kodiak, Alaska. All right, so then what? Okay, so we get rid of the president of the company, and you just said promote the rightmost person in the company. You know, that just seems like a thing. Like, well, president's not there, so we'll just stick whoever's over here. At the lowest level, these are the people least qualified to be running the company, but we'll just take this person and put him in charge. Okay, so let's do that. Okay, further evidence that this is not some sort of illegal act. Well, it's probably illegal to assassinate someone even if it's not a public figure. But definitely there's a more reasonable chain of succession for political office. Anyway, so what we've done with our company is take the rightmost person at the company, fill the position of the president with whoever was last. But now what? Is this a min heap? No. We've got someone underqualified in the president's position. So what do we do?
Boot him out.
Well, demote. Okay, who gets the job when you demote this person? 0. Why 0? Why not 5?
Because 5 is worse than Bob.
Yeah, it's true. So how would you describe it as an algorithm? What do you do? So yeah, so what you do is promote the right to president, then demote repeatedly, always taking the better successor, right? So in this case, we take 0 instead of 1. All right. How about now? Is this a min heap? Yeah, 1's reached a good stopping point. Okay. Yeah.
What's the reason that you promote the rightmost person?
Mm-hmm.
Why don't we just, when there was a negative one, why don't you promote the smaller person on top?
Mm-hmm. Okay, yeah, let's try that out. Let's see. That's a good question. All right, so let's see. What do we have? -1, 0, and 1. This is how things work. Okay, we're time machining our way back to before this tragic event. All right, so here we go. So we have this. So you're proposing what exactly? Say again.
Can we promote the person to my right who's most qualified?
Mm-hmm. So I promote the person. Okay, so you're doing that. Yep. Then what?
And then as you go down, promote
Mm-hmm. One more
to the
time?
right, so continue that.
Yeah, okay. And then delete this.
Yeah.
So this seems fine. So can anybody see where there might be a problem? I didn't see it last lecture, but someone did see it.
It won't be min heap, right?
Oh, well, this is a min heap, though. Check it out.
Yeah, but where did negative 1 go?
It's gone. It was the largest. So that's fine. We want -1 to be gone. Like, this is a great deletion, right? In this particular case, it works.
Not complete.
That's still complete.
Oh.
It's actually correct. This algorithm that you've proposed works for this case. Yeah?
Wait, so like, what happens if, you, like, wait, hold on, never mind.
No, we'll go back to the original. So this is the situation we ran into.
Oh,
So-
I know.
Yeah?
If you end up like in the middle or on the left,
Mhm.
and you remove it, then you kill the completeness.
Yes. All right. So you're saying basically, let's say 0 is here and 5 was here. The reason the strategy you proposed works is because this guy was going to get demoted back to this position. But if this particular tree, this one, if we were to demote -1, where's -1 going to end up? On this, like maybe this position. I don't know, tiebreakers. So we'd have -1 and 0 swap. This is 0. Okay, we got to widen this. Our tree is just getting really lumpy. All right, and then we do it once more. All right. Okay. And so we end up with this, and then if we were to remove -1, we end up with an incomplete tree. Make sense? So the reason yours worked was only because -1 ended up here. Yeah.
Can you redefine complete?
Yes. Complete means that missing items are only at the bottom level, and that if anything's missing, everything's to the far left as possible. Yeah. I know that's not like the most mathy definition, but it's much better than the alternative, I promise. Cool. All right. That's heaps. So, why completeness? Well, obviously one advantage of completeness is what? What's one thing you get out of completeness? Yeah, balance, bushiness, logarithmic behavior. But we already had logarithmic behavior with the BST. So here's the real reason that people use heaps. So remember that trees can either be represented as a linked data structure. We had representations 1A, 1B, and 1C. Or we can represent it as an array. And we left this as some sort of vague, nebulous, like, whoa, moment before. Here's where it comes into play. So let's suppose we have a binary tree represented by an array. This is how I represent my heap of items, right? So there's a bunch of keys here, X, E, J, C, B, G, F, A. So I think it's certainly intuitive to think of position 0 as the root. Who do you suppose the left child should be if this is an array? And we're assuming this is now a complete tree. So who do you think the left child of X should be, given this array? E. That seems kind of natural. Okay, who should the right child of X be, do you think? J. All right. Why? I mean, that's not the only possible interpretation. But if you think about it this way, if you think of this as a tree, if you know it's complete, you can just pretend that what you're doing is reading the level order. Okay. So if you pretend like what this array is the level order traversal of a tree, then you can reconstruct the original tree just given an array. So what will be the left child of E? C. Okay. What's after E? Or what's the right child of E? B. Okay. Left child of J? G. Okay. Right child of J? F. And then where does A go? Yeah. So again, here the goal is just, or the point is, I'm making this up. I'm saying, wouldn't it be cool if that's what an array meant? An array is just a way of thinking about my my tree, right? Because a data structure isn't about how it's held in memory or what the links are or whatever. It's how your data structure behaves when you type in code. So for example, when you guys deleted, let's see, when you delete from, we've certainly had data structures where what deletion meant was just decreasing size by 1. Like whatever number you had in the list is still there. Like with a resizing array, we don't actually zero out the item we delete. We just change the size. Similarly here, it's just, if this is what our code is thinking about, like at any given time, it should behave well. Now, to make that more concrete, I'm going to bring up a cool point, which is a common trick to make things it's a little cute, perhaps too cute. But often what we'll do is, instead of representing a tree by an array that starts at position 0, we're going to leave the 0th position empty. And then we're going to put the root in position 1 and so forth. Now the reason for this is that if I'm writing code and I want to find, say, the left child of, let's say, E, so if E is in position 2, where's the left child of E? What position number? 4, right? Where's the left child of C? Looking over here. 8. So the left child is always what, do we observe? Times 2. And it really does keep working. So if you represent a tree like this, then if you want to know the left child of a specific point, you don't have to keep around, actually I should say, in a normal tree, how do you know where the left child is? It's the homework 6 when you guys wrote the VST class or whatever. How did you know where to get the left child data from? Not less than. You had to get like a, somebody said less than. Field, yeah, a field named what? Left, right? You had an explicit address. For every node, you had a left and a right that said, if you have this item, this is where you find my left child. This is where you find my right child. By using an array, this is the whole point, is that we avoid the need for a left and a right pointer. Instead, if I know where something is, I'm in position 2, then I know the left child is in position 4. We're sort of arranging the data in a way so that everything is exactly where we expect it to be, and we don't have to actually look it up, right? And likewise, the right child is just k times 2 plus 1. Now, if you want to, if you don't like this being too cute thing, you can start at position 0. It just makes this formula a little more complicated. I think you have to subtract 1 or something, but this just seems nicer. All right. So I love this trick. It's a very cute one, but it begins bordering on the range where, while you do get, it becomes only arguably simpler, right? Because some people find this annoying, but to think about. But I don't know. Yeah, there's a rule in programming which is don't try to be too cute, but this seems to have passed muster with the hackers of yore who implemented heaps like this all the time. Yeah, so there you go. That's the story of heap representations. Yeah? Oh, no. All right. Yeah. Any thoughts about this thing? Okay. Okay, so now let's talk about implementations of these priority queues. And actually, I should take this old slide back. We'll bring it here, color it in, bring our caveat over. No, okay. We haven't got our colors back. Cool. Okay. So let's talk about the heap representation then. So if we're doing heaps the way we've just described, what do you suppose the runtime is to add? So adding consists of sticking them in the bottom position and then promoting them over and over. Log in, right? So you got to do in swaps. It's perfectly balanced, so we should just have to go log in. How about getting the smallest thing? 1, okay? How about removing the smallest? All right. So question back to you then. As far as these logins go, how do you know, if we have an array like this, how do we know where the add should be? So how do you know that the next thing is going to go here? Just imagine. So how do you know the 9? Where do you get the 9 in the 9? Length? Okay, that's an interesting thought. So you've suggested that what we do is look at the array length and say, what is the length, and then add or subtract. We'll see. In this case, the array length is, it would be length minus 1, right? I guess, or the length. So if we use an array that's exactly this length, how long will it take to insert something? Why? Yeah, you have to copy everything. So if I have an array that's only of size 9, that is, it has 0, 1, 2, 3, 4, 5, 6, 7, 8, or 9 things, we have to actually create a new array and make copies. So what's a better strategy than that? Resize, yeah. So there's actually a secret resizing here I haven't been telling you about. When you have arrays, there's really some resizing going on. So what do you suppose your strategy should be? When should you resize? What's that? Load. You could do it as a load factor, though. When you guys did resizing arrays for homework 5 with the resizing array map, I don't remember if that's what you did. When did we do a resizing array? We did do a resizing array at some point. What's that? Yeah, that one we didn't resize though. This is the one that was the annoying generics homework. When did we resize? So the load factor thing's an interesting point. But I'm going to say that, is there any disadvantage of having a... What's the load factor where you should resize?
Yeah, that's right.
Yeah, 1, right? So once it gets full, then you resize. Okay. How much should you resize it by? Yeah, probably 2 times, some geometric factor. And then remove smallest, we might resize down as well. So I'll make a note that the heap is login time amortized. Okay, so occasionally it'll be longer. Some resizes, but no big deal. All right, so it's amortized login. That's cool. Okay, other notes. What good is a heap? So if we compare heaps and BSTs, well, I guess first I should note, how would we make a BST have constant time get smallest? So I give you a homework. The homework is, okay, make a priority queue, and I want get smallest to be constant time. What could you do?
Just keep the pointer.
Yeah, so you could, BST can have constant get smallest if you keep pointer to smallest. So every time you add, update the pointer. When you remove smallest, update it again. So that's fine. One more interesting note then. So what good is a heap? Anybody having a sense of what the advantages might be, if any? Memory, yeah. So heaps take less memory. So a heap has one single reference per every single item. In fact, if we're not going to go through the code, but if you're curious, you can look and see an implementation of a heap here. So what it does, let's see, it has just an array of what are called keys. So this array of keys, where key is some generic type, each one of these is going to be, if you're on a 32-bit machine, it'll just be 32 bits for a pointer. Whereas with a tree, how many pointers do you need for each node? Like a binary tree. 3. 1 for the item, 1 for the left, 1 for the right. So you use about 1/3 as much memory. About 1/3 the memory. Is it faster or is it slower? This is unclear. You would have to do some kind of tests. Okay. All right. Any other thoughts about heapsies, as I call them? All right. So a couple of questions just to round out, make sure we understand what's going on. So how does a priority queue know how to determine which item is larger when you do the adding, when you try and do this promotion, swapping, demotion? Comparable, okay?
Comparator, or you can when you comparator.
Okay, good point, yeah. So if we look at our API here, if we wanted to make it a comparable, what's missing from this API specification? Yeah, so we need a type bound. So what's interesting is the Princeton library does not do that. Theirs, it is a min PQ of key. They do not do type bounds. We didn't at Princeton do as much generic stuff as we do here, so we ignored that. Instead, what we did is, ignored this for a moment, this was the approach we used, which was to take the item, and what's going on here? It's casting it as a comparable. Why is this potentially dangerous?
What if it isn't?
It might not be a comparable. Then your priority queue will crash at runtime. Okay, so we avoided type there's always this trade-off in teaching. Tell you too much or give you industrial strength code. We tend to err on the side of more realism here to some consternation for you guys. Okay. Now, to your other point, what's the downside of using comparable? Or rather, suppose we wanted to compare things not just based on their mass, maybe, but also the length of the description of them. How would we modify our priority queue API to allow for different orderings? What do you think? So you might not be able to, how would we modify, maybe not min-pq, but the implementation? That's kind of a tricky question. So I want to order things not just on one ordering, but perhaps many. Yeah.
Well, when you add, you have to look at the first characteristic, and then you have ties.
Okay, so you're basically saying that we would rely on a more complex compare to method. But let's suppose I want to insert strings and sort them based on order of the number of z's. Yeah. Yeah, comparator. Okay. So how?
Constructor.
So we need a constructor that takes a comparator as an argument. And in fact, that's the approach that the Java standard library uses, and indeed this Princeton one does as well. So if you look at the constructors, there's one that does just that. Okay, where'd it go? Constructor. I don't know. Why did I search for constructor? It's a long day. Anyway, wow. Yeah. Anyway, yeah. Aha. I was hoping for magic, but I like your theory about my thinking instead. Okay, so in this case, it takes a comparator as an argument. All right. Do we dare? Yeah. We'll dip our toes a little bit into the summary. Okay, so any more thoughts about this before we do 2.5 minutes of summary?
So if
Yeah.
there's no comparator, does that mean that if it's like meaningless?
Say again?
Like if there's no comparator, right? Like does that mean heap is meaningless?
Heap is meaningless. Oh, if there's no comparator or comparable, it is indeed meaningless. So it requires ordered items, just like BSTs do.
Okay.
Yep. So you need some sort of ordering somehow. Cool. All right. So, all right. We're going to roll most of this into Wednesday, but yeah. Oh no, running out of space. Well, it's okay. We only have 1 more minute, so we'll just cross our fingers. We're using up my disk space aggressively by recording this. So given a stream of data, retrieving information of interest is most of what we've done for the last 3 weeks. So for example, suppose you have some cool social networking site like here, Friendster, which I never used. Yeah, so website, you have some users put some information up and I only want my friends to be able to see it. So the data structures we talked about, like maps and sets and so forth, those are the things that enable these things to be possible. Or, as you guys saw in Project 1, the idea of taking a bunch of data and putting it in some useful data structures so you can make beautiful visualizations is quite nice. And in all of those cases, you're always throwing things in different kinds of bags and asking those bags, hey, give me what I want. So this will be our closing one, I think, of the day. So I would say that there are 4 primary abstract data types that fulfill this narrative. The first is the list, and I'll give this one away for free. So in that one, what we do is we have a list, and we say, list, here you go, here's a new thing. I add an item, a key, we'll say, and I retrieve things by asking the list, give me the thing in index, say, 7 or 10 or 15. And then finally, and when we ask, what are we actually retrieving by? What's the thing we're looking at? We're looking at the index of the thing. So what's another one of our data structures? Map. All right. So in that case, when you add something, what do you do? Yeah. And what's the word Java uses for this one? Put. Key value. Now when you ask for something from a map, what do? Get key. And so in this case, I'd say we're retrieving by key identity. So I say, what is the value that goes with this particular key? That's just the way I'm putting it in English. Okay, what's another type of these? Set, all right?